Hey everyone, welcome back to my channel AI Connect Grow. In our last video, we introduced you to transformers and discussed their key components. The link to that video is in the description below. Today, we are diving into two essential concepts in transformers: input embedding and positional encoding. These are the foundational steps that helps transformers convert words into meaningful numerical representations while keeping track of their order in a sentence. By the end of this video, you will not only have a deeper understanding of these concepts, but will also learn how to implement them using PyTorch code. Let's dive in and understand input embedding and positional encoding. If you go to my website aiconnectgrow.com, you'll be able to find all my videos over here and the corresponding blogs to it. This is the blog part 2 transformers, input embedding and positional encoding, which you can use as a reading or a revision material once you are done watching this video completely. Because here in this particular video, I'll be explaining how input embedding and positional encoding works in detail in transformers and how to implement it using PyTorch code. Before we go ahead and implement input embedding and positional encoding using PyTorch code, let's understand how these two together work in transformers. This is the image that I've created so that I can explain you input embedding and positional encoding in a very simple way. So let's start with a very simple example. So here in this particular example, I have taken two sentences. Transformers are very and I do love programming. So these are the two sentences that we have in our example. Let's see how these raw sentences are converted into numerical representation, which is going to be passed to the transformer model. The first step is to apply tokenization. So what is tokenization? Tokenization is the process of dividing text into smaller units called tokens, which can be words, subwords, or characters. The choice of tokenization depends on the task and the language being processed. Here we have used word level tokenization, wherein the text transformers are very powerful, are tokenized as transformers as one token, are as one token, very as one token, and powerful as one token, because we are treating each word as single token over here since we have chosen word level tokenization. In case if you would have chosen subword level tokenization, then transformers could have been treated as trans as one token and formers as one token. So this is how the tokenization is applied. So now that the tokenization is done, the next step is indexing, wherein we map tokens to integers. Since a machine can't directly understand words or tokens as they appear in text, this mapping is typically performed by creating a vocabulary. So how do we create this word vocabulary? This is usually done by sorting tokens based on their frequency in descending order. That is, most frequent tokens comes first. For example, if your vocabulary size is 50,000 tokens, then the most frequent 50,000 tokens are added to the vocabulary. Along with these tokens, sometimes models that use transformers require additional special tokens to indicate structure, such as CLS, classify token, which indicates the start of a sequence, and separator, which is used to separate two sentences, may be used in question answering task. And also we have other tokens such as pad. This is used for padding sequences to same length, basically to process multiple sequences in parallel, like for example in batching. Shorter sequences are padded to match the length of the longest sequence in the batch, because we need all the sequences to be of the same length. Then the next one is mask. Mask tokens are for masked language modeling, for example BERT, which I'll discuss more in detail in my upcoming sessions when I discuss about BERT models. So these special tokens are often assigned integers like 0, 1, 2, and 3 to ensure they are prioritized. Once the integer is assigned to special tokens, The remaining tokens, like word tokens over here, are assigned consecutive integers based on their order in the frequency sorted vocabulary. This is how we map the tokens into integers. So far we learned about tokenization and indexing. But these indices are not sufficient enough to learn the context between these words because these integers were created based on the word frequencies, which was required to represent the words in a numerical format so that we can send this as input to the embedding layer to learn the dimensional vectors, which can be used to learn the context between the words. Now that we have this matrix of size 2 samples and 4 sequence length, because we have 2 samples over here, transformers are very powerful and I do love programming. And we have 4 words in each of these samples. Hence we have a matrix size of 2 samples and 4 sequence length. Whereas in real use cases, the batch size can be of 32 samples or 64 samples or 256 samples, etc. And the sequence length can be 256, 512, etc. This batch of input sequences of size, batch and sequence length are sent to the embedding layer. This allows the model to process multiple sequences at once. Instead of processing each sequence one by one, batching them together speeds up computation by leveraging parallel processing. This is particularly useful when training on large datasets as it allows the model to learn from many examples simultaneously. To handle sentences of varying lengths, shorter sequences are padded with a special token. Example, a padding token like 0, so that all sequences in a batch are of the same length. The embedding layer is a neural network layer that maps tokens into continuous dense vector representations called embeddings. The embedding layer uses an embedding matrix, which is a dense matrix of dimensions V into D, where V is the size of the vocabulary and D is the embedding dimension. Each row in the embedding matrix corresponds to a token over here. The ideal embedding dimension in transformers depends on several factors such as the size of your vocabulary, the complexity of your task, and the available computational resources. Popular transformer models have predefined embedding dimensions based on extensive experimentation and performance consideration. For example, BERT base uses 768 as embedding vector dimension and GPT-3 uses 2048 as embedding vector dimension. This embedding matrix is usually initialized with random values, often generated using methods like uniform distribution or normal distributions. During training, the model adjusts the embedding vectors through backpropagation based on the loss function to learn meaningful representation of the tokens. For example, in a sentiment analysis task, words like happy, joyful, and content might have embeddings that cluster closely in the vector space. Meanwhile, words like sad or angry would be distinct distance clusters. This semantic organization allows the models to generalize better when making predictions. Now that the embedding vectors are trained, the embedding matrix effectively functions as a lookup table, wherein each token's index maps to its corresponding embedding vector. This helps us in retrieving the embedding vectors based on the index directly from this lookup table, which is computationally more efficient instead of using sparse vectors like one-hot encoding. Once these embedding weights are learned here in embedding layer, the output from the embedding layer is of shape, batch size, sequence length, and embedding dimension. Here in this example, 2 corresponds to 2 samples that we have taken. Transformers are very powerful and I do love programming. 4 corresponds to each token in each of the sequences. 3 corresponds to the embedding dimension. In the embedding layer, we learn this embedding matrix wherein we learn the embedding vector for each of the vocabulary. And the final output that we got is for each of the words, transformers are very powerful. We have learned an embedding vector of size 3, which is now able to understand the context between the words in the sequence, which can be seen in this matrix as well. For the token transformers, which is this particular token, it is being represented as 3-dimensional vector. And for the next token over here, which is R, it is being represented as three-dimensional vector. And for the next token very, it is being represented as three-dimensional token. And similarly for powerful. And for the next sentence, for I, again it has three-dimensional vector, which we are not able to see over here. And similarly, do, love, programming. We can see over here for the programming token, it also has a three-dimensional vector. Similarly, when we have millions of sequences, we can imagine how for each of the sequences, based on the sequence length that we have chosen, we can get the embedding dimensional vectors. This is a whole idea how the input embedding works. Next, let's understand how to create positional encodings and then append it with input embeddings and send it as an input to encoder in transformers. So why do we need position encoding? We've already seen how each of the words here in each of these sequences are simultaneously sent into the embedding layer and processed parallelly. So the input lacks information about the order of the words in the sequence. For example, if I give a sentence like I eat pizza and the next sentence as pizza eat I, both of these sentences are going to get similar input embedding, which may confuse the model in understanding the relationships of tokens in a sentence. So how do we add the information regarding position of words to input embedding? Can we just use integers like 1, 2, 3, 4 in order to represent the order of the sequence and append it to the input embedding layer? No, because these single scalar values per position lacks the rich multidimensional information needed for transformers. And also simple numbering doesn't provide continuous patterns, making it harder for the model to learn positional relationships. If not scalar value, can we use binary numbers? No, binary numbers don't capture the relative distance between positions in the embedding vectors, making it difficult for the model to understand token relationships. And they don't scale well for longer sequences. In the paper Attention is All You Need, wherein the transformers were introduced, they have shown how positional encoding can be implemented using simple sine and cosine functions. First, let's look at the sine and cosine wave diagram. You can see that these two waves are periodic and oscillatory, meaning they repeat their values over time, making them ideal for representing positions in sequences of varying lengths. This periodicity allows transformers to generalize well to sequence lengths not seen during training. And it also captures the absolute and relative positional information. This allows the model to capture the relationships between tokens based on their position. Now let's assume that we have two different words and each of these words are embedded into four-dimensional vector. Using this sine and cosine formula wherein pos stands for position in the sequence, zeroth position, first position of the words. D model stands for embedding dimension. Here it is four-dimensional vector. And I stands for index of the dimension. Like within this embedding vector, we have zeroth index, first index, second index, so on. By substituting these values here in the formula, we create these positional encoder vectors which are of the same dimension as the input embedding vectors. Here in the positional encoding vectors, the even indices makes use of sine function, which we can see over here, and the odd indices makes use of cosine function, which we can see over here, assigning a unique representation to each position in a sequence. Finally, these positional encoding vectors are added with the word embedding vectors, which makes it aware of both the token's meaning and position. Now that we have positional encoding vectors, it is added with the word embedding vectors and sent as input to the transformers. Now let's summarize whatever we just discussed so far. We understood like how we can take these sentences, split them into tokens and then do the indexing. Once we have this batch of sequences which are indexed, we send it as an input to the input embedding layer and then get the embedding vectors for each of these words. Once we are done creating the input embedding vectors, we also learned how to add the order of sequences using positional encoding, which makes use of sine and cosine function as discussed in Attention is All We Need Transformers paper. Once these positional encodings are created, we add it with input embedding vectors and then send it as an input to transformers. This is how the whole input embedding and positional encoding works together. Whatever I explained so far regarding input embedding and positional encoding, I have put it all over here in this particular blog so that you can use this as a reading or revision material. Thank you so much. Have a good day. Please do subscribe and support me so that I can create even more better videos for you.